Welcome to this explainer. Today, we are going to completely demystify the complex digital journey of the Mercedes-Benz Actros MP3 vehicle speed signal. So whether you're a diesel mechanic, an automotive engineering student, or honestly just someone fascinated by modern truck architecture, you are absolutely in the right place. We're going to virtually strip this truck down and visualize the entire signal path, tracing it from the physical sensor all the way to every single system that relies on that data.
Right out of the gate, let's just go ahead and shatter a huge myth. If you're expecting to find a simple, direct wire running from the transmission straight up to the speedometer needle, well, you're in for a big surprise. In modern heavy commercial trucks, that simple analog reality, it's completely gone. You see, on older vehicles, it really was just an electrical current moving a physical magnet. But on the Actros MP3, this signal is heavily processed, cryptographically secured, and shared across a massive digital network way before you ever see that needle sweep across your dash. It's really less like a traditional wire and, honestly, a lot more like a highly secured data packet flying through a rolling data center. To build a solid mental wiring diagram of this architecture, we're going to track the signal through 5 key stages. First up, the B18 sensor, then the tachograph gateway, third, the VCAN network, fourth, the signal consumers, and we'll wrap up with redundancy and diagnostics. All right, let's jump into stage 1, the B18 sensor and signal generation. If we strip away the truck body and zoom right into the transmission output housing, you'll find the B18 sensor. Mercedes calls this the travel and speed sensor, or Weg- and Geschwindigkeit sensor. It's usually a Kita's 27171 series. And wow, this is a massive leap from those older 2-pin inductive sensors that just spat out a raw, dumb sine wave. The Kitas is an active, magnetoresistive Hall sensor, which means it actually sends encrypted digital data. It doesn't just passively measure speed, it actively talks to the truck via a highly secure interface. Now, for the technicians out there wrenching on these, pay close attention to this 4-pin setup. You've got your ground on pin 2, a real-time square wave speed pulse on pin 3, and that encrypted data line on pin 4. But check out pin 1. That is an 8-volt power supply coming directly from the tachographer. This is a critical warning. If you're troubleshooting and you poke pin 1 with a standard 24-volt test light, yeah, you will instantly fry the module. Always remember, it's 8 volts. So how is that raw signal actually born before all the encryption happens? Well, inside the gearbox, there's a toothed reluctor wheel. As the output shaft spins, those metal teeth fly past the tip of the sensor. The changing magnetic fields flip the Hall element inside and boom, it fires a perfectly clean rectangular electrical pulse down the yellow sensor cable. It typically generates exactly 8 pulses for every single revolution of that gear. That pulse frequency gives us our speed, and the total pulse count, that gives us our distance. Moving right along to stage 2, the tachograph, which acts as the master gateway. If you follow that yellow sensor cable up into the cab, those 4 wires do not go to the dashboard cluster. Nope, they route directly to the true boss of the entire system, behind the center dash, the DTCO 1381 tachographer. Because heavy commercial vehicles require incredibly strict legal monitoring for driver hours, the tachographer is the ultimate gatekeeper. Every single other system on the truck that needs speed data, it has to ask the tachographer for it. Inside the tachograph's processor, a really rigorous verification happens. It takes that physical square wave pulse on pin 3 and constantly compares it to the encrypted digital data streaming in on pin 4. Think of it like checking a security ID badge against someone's actual face. If those 2 things don't match perfectly, the tachograph instantly logs a tampering fault and flatlines your speed reading to 0. But if it's a match, it calculates the real speed using programmed factors like your tire size and broadcasts that verified data out to the network. Which brings us to stage 3, the VCAN, the truck's digital nervous system. Picture the truck going completely transparent, revealing all these glowing color-coded lines. Those are your twisted pairs of CAN bus wires. The tachographer takes that verified speed, digitizes it, and blasts it simultaneously across these networks. We're talking the blue exterior CAN, the green interior CAN, the orange frame CAN, the red drivetrain CAN, the purple brakes CAN, and the white diagnostic CAN. What was once physical rotation is now just a line of code flying around at lightning speed, stamped with the vehicle speed, a timestamp, and a source ID. Now for stage 4, the consumers of the speed signal. And here is where we totally bust that opening myth. When you look at your dashboard, the instrument cluster, the A1 ICU module, it's actually just another node on this vast network.
It just grabs the data packet from the green CAN2 line and translates that digital number into the electrical current needed to sweep the physical needle up the dial. Again, zero direct wiring from the transmission. If that CAN bus goes down, your needle drops dead, even if the sensor on the gearbox is working perfectly. If you look at an overview of who is actually grabbing this data off the network, you can see it's heavily split. About 40% of the modules are powertrain and drive systems, keeping you moving efficiently. Another 40% are braking and safety systems, keeping you alive. And the final 20% handle chassis and comfort features. Let's put this into perspective because it's pretty wild. The engine control module, or MCM, uses this exact data to enforce the 90 kilometers per hour top speed limiter by cutting fuel. The transmission control calculates its automated gear shifts based on it. The electronic brake system uses it to figure out how aggressively to engage the retarder. Even the level control module is listening in, so it can automatically hunker the truck's chassis down at highway speeds for better aerodynamics. Literally, one single sensor failure on the back of the gearbox can trigger 15 different system failures. Finally, we hit stage 5, redundancy and diagnostics. Mercedes-Benz engineers knew they couldn't just let an 80,000-pound truck die on the highway because a single wire chafed, right? So redundancy is absolutely crucial here. While the tachograph is the primary, legally sealed record, the electronic brake system, the EBS, actually has its own independent wheel hub sensors. If the B18 sensor fails and those main network lines go dark, the purple EBS wheel sensor lines light up as a backup. The truck's computers seamlessly switch to reading the approximate speed from the wheels. It keeps you rolling, though your dash will definitely light up with warnings. When you do hook up your laptop to the diagnostic socket, these are the heavy hitters you'll likely see. Code 23408 means the signal is implausible, which usually causes the speedo to drop out randomly. Code 23224 tells you the tachograph signal is completely missing from the CAN bus. And 3682, that's an engine management fault that will instantly kill your cruise control and throw you right into limp mode. These codes are great because they immediately tell a tech if they're fighting the sensor, the tachograph itself, or the engine management system. Let's run through an optimal 15-minute diagnostic sequence. This should be standard operating procedure. Minute 1, always, and I mean always, look at the tachograph screen directly first. If the tachograph shows your speed while you're driving, but the dashboard shows 0, you've got a CAN bus communication problem, not a sensor problem. Stop right there. Don't go crawling under the truck. If the TCO does show 0, by minute 5, you should be verifying that 8-volt power at the key test sensor. And by minute 15, use your software to compare the tachograph speed against the EBS wheel speed to hunt for any massive mismatch. Before we wrap up, I want to highlight a massive warning straight from the diagnostic manuals. Never try to bypass a KITA sensor with a signal generator to cheat the tachographer. Because this isn't just a raw pulse. Trying to trick it breaks that cryptographic handshake we talked about. The tachographer will catch it instantly, log a manipulation fault, and lock the truck into a brutal 40 km/h limp mode. Just don't do it. We've just seen how a simple measurement of a spinning gear inside a transmission has evolved into a heavily guarded, encrypted digital secret that feeds an entire network of advanced modules. It really is a masterpiece of modern automotive engineering. But it leaves us with a pretty wild thought. As these commercial trucks become literal rolling data centers, what basic mechanical part will they lock down and encrypt next? Think about it. Thanks for joining me on this explainer, and I'll catch you next time.